Maxwell's Equations and Electromagnetic Waves. James Clerk Maxwell put together the major concepts of electricity and magnetism in 1861, provided a mathematical formalism, and added the last term to Ampere's law. Nobel laureate Richard Feynman stated, "From a long view of the history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. The American Civil War will pale into provincial insignificance in comparison with this important scientific event of the same decade." Here are the equations. You don't need to know them in this form until AP Physics C, but they're nice to look at, and you can maybe see the equations you've already learned in this course in a slightly different notation. Thus far, we have modeled various observed phenomena of light. Now let's consider the fundamental nature of light. We already know that Ampere's law states that a current caused by an electric field generates a magnetic field. We also know that Faraday's law states that a changing magnetic field generates an electric field. Together, these laws tell us that a changing electric field would create a changing magnetic field, which in turn would create a changing electric field, which would create a changing magnetic field, and so on. These time-varying fields travel as electromagnetic waves. The electric and magnetic wave segments of an electromagnetic wave are perpendicular to each other and to the direction of propagation. We have an electric field, I'll do this in red, propagating in this dimension, creating a magnetic field that's perpendicular in this direction, and they're traveling in this direction, which is also perpendicular to either one of those dimensions. Here's an example of how an electromagnetic wave is created. In a broadcast radio or TV antenna oriented on the vertical z-axis here, electrons are accelerated up and down. See this dot here? They're accelerated up and down by a changing voltage. As the electrons accelerate, they create a changing electric field in the z direction. This creates a changing magnetic field in the xy plane, shown in blue. These initial magnetic and electric fields propagate to the right along the y-axis and would get really small very quickly due to their 1 over r squared and 1 over r dependence. But because these are changing fields, they keep creating their partner field, which creates an electromagnetic wave which will keep going until absorbed by some material. The solutions to Maxwell's equations showed that the speed of an electromagnetic wave in a vacuum is 3 times 10 to the 8th meters per second. This was also measured to be the speed of light. It was realized that light is an electromagnetic wave. There is also a very interesting relationship between the electrical permittivity and magnetic permeability constants. C equals 1 over the square root of epsilon naught mu naught. Look, so we plug in the constants into this equation and we get the speed of light. That 3 times 10 to the 8th meters per second is the speed of light in a vacuum. The electric field vectors of an electromagnetic wave are in a plane perpendicular to the direction of motion of the wave, called the plane of polarization. Light waves emitted by the sun have random polarizations. The light is said to be unpolarized. Most of light's interaction with matter is due to the electric field vector. Some long organic polymers allow electrons to freely move along their lengths. When the electric field of an electromagnetic wave is parallel to the polymer's length, it accelerates the electrons in the polymer. Thereby, it's losing energy and decreasing its magnitude in that direction. Electric field components that are perpendicular to this axis are unaffected, since the electrons in the polymer cannot move in this direction. In this case, the electric field component of the wave loses no energy as it passes through. Practical applications of this include sunglasses and light filters. Unpolarized light enters from the left. The sheet of polymers only allows light through that is perpendicular to its molecular chain, polarizing the light in the vertical direction. Only transverse waves can be polarized. Longitudinal waves cannot be polarized. Polarizing sunglasses contain a polarizing filter that blocks horizontally polarized light. Since light that reflects off of water and other horizontal surfaces is mainly horizontally polarized, this light is blocked. The polarizing filter reduces the intensity of the unpolarized light to 1/2 the original intensity. The glare is also reduced without losing any of the details of the observations. Here, we have two polarizing filters arranged that will block all of the light rays. So here we have unpolarized light, then it's polarized into this direction, but then it's passed through another filter that's tilted 90 degrees on its side, so no light is going to make it through. The intensity of the light can be reduced further by a second polarizer at an angle theta between the polarizer axis and the plane of polarization. The light striking the second polarizer has already been polarized, and its intensity is represented by I0, which is half the intensity of the original unpolarized light. Because the intensity of a light beam is proportional to the square of the amplitude, the intensity of a plane polarized beam transmitted by the second polarizer is given by this equation. Be careful solving polarization problems. The first polarizer cuts the intensity in half. The second polarizer reduces it by cosine theta squared. This equation is not on the AP Physics 2 equation sheet, but theoretically they could give you this equation and ask you to solve a problem with it.